Hello. Hello, everyone. My name is Yuntian. I'm from Harvard University, and the talk I'm going to talk about is about a use case of using OpenMT for non-neural machine translation. So the title of my talk is Image to Markup Generation with Cost to Fine Attention. This is a joint work with Ansi from University of Eastern Finland and Jeffrey, who used to work in our lab, and my advisor, Professor Rush. So here is an overview of my talk. And first of all, I'm going to talk about the problem definition. And then I'll introduce our dataset, which enables training an end-to-end neural system. And then I'll talk about the model. And lastly, I'll talk about the experiments we conducted. So why do we care about multimodal generation? Below is a quote from Professor Robert Deng. Real text is not disembodied, it always appears in context. As soon as we begin to consider the generation of text in context, we immediately have to consider issues of typography and orthography and prosody. This is perhaps most obvious in the case of systems that generate both text and graphics and attempt to combine these in sensible ways. So there have been well-established tasks of image to text. So one of them is natural OCR, where the goal is to recognize the text from an image. And another one is image captioning, where the goal is to generate a caption describing what's going on in an image. But both of them are different from the task I'm going to talk about, in that in image to markup, just some problem with this animation, but basically the task is given an image of a formula. The goal is to generate the text that can render it. So the difference of this task from the previous two tasks is that the output is also structured because the text can both encode the content as well as the structure. So in order to train an end-to-end neural system, we generally need a large amount of training data. And unfortunately, previously, the largest available image text dataset is only a few thousand examples. So we constructed a dataset of our own. And here are a few examples taken from our dataset. So the dataset is quite challenging. There are long formulas, there are multi-line equations, integrals, arrays, fractions. So this dataset is developed by ANSI, and it was originally used for OpenNI requests for research. And the dataset is extracted from LaTeX sources of archive papers, and we render that in a vanilla LaTeX environment. The table shows the basic statistics of our dataset. So we have around 100,000 examples, and the median length of the LaTeX formula is around 100. So now that we have a dataset, we directly applied a model developed by Kevin Xu, which is widely used in image captioning on this task. So the model consists of an encoder, which is a convolutional neural network to encode image features, and a decoder, which is an RNN with attention, to generate the output LaTeX sequence. And we train this model by maximize the log likelihood of the LaTeX sequence. So we modified the model a little bit to reflect a difference of our task and image captioning, in that we typically write formulas in a left to right order. So we believe that position information is really important for this task. So to reflect our assumption, we added an additional row encoder, where we add a recurrent neural network running from left to right in both directions on top of the CNN feature map to explicitly encode positional information. And later on, I'll show you the experiments that validate our assumption that this is indeed important for this kind of task. So here, let's take a deeper look of how the model works. So here I show an intermediate step of generation. So at this stage, the decoder first assign attention weights to the whole image. I show the attention weights by the intensity of the red color. So note that actually we are using a softmax to generate the attention weights. So although it appears that only 2 cells here are red, actually there are non-zero weights everywhere in the image. And based on the attention weights, we take a weighted average of the image features and classify the current symbol. So this is one step of generation. So although our model works quite successfully on this data set, there is a potential problem of applying this model to larger images, because at each decoding step, we need to attend to the whole image, and the attention complexity grows with the area of the image. So if we want to use our model for larger images like a whole document, this could be pretty prohibitive in computational complexity. So therefore, we present cost to fine attention, which reflects an intuition that at a certain decoding step, actually it's pretty easy to locate the rough region where the next symbol is likely to appear. So in addition to the cost, in addition to the original high resolution image feature map, we superimpose a coarse grid. And at a given decoding step, we first select a blue cell which we believe the next symbol is likely to appear, and then we only attend to the cells, to the high resolution image inside this blue cell. So by doing that, we can reduce the attention complexity pretty much. So in the previous case, during each step of the decoding, we need to attend all over the smaller cells. So in this particular case, there are over 100 such cells. But if we first select a blue cell, and then we only need to consider the small cells inside that, we only need to first look at 12 blue cells, and then only the 16 smaller cells inside that. So which by doing which we can reduce the complexity pretty much. So to reflect our intuition, to implement that in our model, we first, for notational issue, we first rename our previous features as fine features, so which correspond to the smaller cells in the previous slide. And on top of the CN feature map, we add several layers of pooling to get a smaller feature map, which represents a feature map of a lower resolution. And at each decoding step, we first attend to the to a lower resolution feature map. We select a point where we believe the next symbol is likely to appear, and then we only consider the cells within that region. So we cannot directly train this model with backpropagation, because by selecting a cell in the coarse feature map, we are essentially using an operation that's non-differentiable. So in order to train that, we have to use algorithms like reinforce. And an alternative is to use a sparse activation function when we are selecting the a point from the lower resolution feature map, like sparse max. But a potential problem might be there is no guarantee that we will end up with only one particular cell with a non-zero attention weights. So here are our experiments. We first tokenize and normalize the latex formulas And since there are inherent ambiguities of the text, we evaluate our model by rendering our prediction and compare it against the original image. And if they are the same, we consider that a match. We implemented our model in OpenMT. So here we show the baseline results. CDC represents a commonly used system in natural OCR, which assumes the left-to-right writing order, which is incorrect in our LaTeX case, since in LaTeX we have fractions or arrays. So it got a poor performance. And we also report a commercial system, Infinity Reader, which is slightly better. By using an end-to-end trained neural system, we got a pretty much decent performance. And by incorporating the row encoders to encode the positional information explicitly, we increased the accuracy by 20%. And here we show the results of our coarse-to-fine attention layer. So here I show the complexity of attention by the average number of cells that the decoder need to look at each time step. So here I show the baseline model where there are no coarse, there is no such a coarse feature map, so there are 0 coarse cells that you need to look at. But on average, at each time step, the decoder needs to look at over 300 small cells to take a weighted average to generate the context vector. And if we only use the coarse cell, although we reduce the complexity, but we get a really poor performance, which means we really need a higher resolution feature map in order to do this task successfully. And here, I also present a result. So coarse and fine reflects the case that if we do the hierarchical decomposition of attention weights, what will happen? So we do not get any computational side benefits, but this provides the upper bound for the coarse-to-fine experiments that I'm going to talk about. With the sparse activation function, since there are many coarse locations that we do not need to look at, the number of fine cells, the number of smaller cells we need to look at, reduce greatly, but we lose the accuracy by around 1%. And our reinforced variant needs to look at only 1 coarse cell per decoding step. So the computation complexity is lowest, but it's at the cost of a lower accuracy. Here are some results, some common mistakes throughout the data set. So the red denotes the ground truth, and the blue denotes the model's prediction. And we can find that although the model makes around 20% error, the errors are pretty minor. So we also apply our model to a handwritten data set. So for the same reason I talked about, we need a large data set in order to train an end-to-end system. Therefore, we synthesize a handwritten data set by replacing the characters in the original data set with handwritten characters. So this is the synthetic handwritten data set. It's different from human handwriting. And we fine-tuned a Chrome data set and compared it with previous systems. And we got pretty competitive results. More details can be found in our paper. So basically, I presented a data set in mutual LaTeX 100,000, which is pretty diverse and challenging. And we present a case study of OCR. And our presented coarse-to-fine attention can be applied to other tasks, like document summarization. So this code is now integrated as part of OpenNLP, and there is a visualization site shown here. Thanks, and I'd like to take questions.
Thanks for the presentation. I'm not sure, but is it easy like to get LaTeX? Because like I can write LaTeX in any LaTeX software, and I can get the image, for example, right?
Mhm.
So I think there's easy way like to generate data from LaTeX to images. Uh, like, can you create data this way, like to increase the size of your data set or so? Like, yeah,
Oh, thanks for your question. So that's exactly the way we generated our data set.
the original data set. Yeah.
Yes, but in order to make our data set more realistic, we took real archive source code.
Yeah.
And we extracted the formulas from that, and we compare that to generate the images. So that's how we constructed our data set.
Yeah, thanks for
Some
the
progression.
clarification. Yeah, thank you.
Yes, thank you for the nice talk. These LaTeX formulas, they are highly structured, no? They are quite structured. They actually they respect some implicit grammar in a way, no?
Yep.
And so, do you find some cases where by exploiting these structural constraints, you could improve your results? You don't exploit them, right? But you might. And actually, we did some work on semantic parsing to logical forms in which we exploit the grammar of the logical forms, and there may be connections with this problem that I'm raising.
Thanks for our question. I think that's a good point. I think if we have limited data, maybe that's very important. But for our model, we found that over nearly all cases, the generated text of our model is valid and can be compiled. So this demonstrates that LSTMs are really good at learning a language model for modeling the syntax of a markup language. But I think I agree that if we have limited data, it's important to impose such constraints. Thanks.